So week number 8 is another solution approach to LP problems. This is the Big M technique. So in the simplex method, constraints that have inequality signs of less than or equal to are converted into its standard form by adding positive slack variables to the left-hand side of the constraint. For ill-behaved LPs, or those LPs with constraints of the form greater than or equal to and or equal sign, we will use artificial variables. These variables will play the role of slack in the first iterations, but since they are said to be artificial, they have to be disposed at later iterations. So for the solution, we will use example number 7, Orange by Bevco. This is from Module 2. So Bevco manufactures an orange-flavored soft drink called Orange by combining orange soda and orange juice. Each ounce of orange soda contains 0.5 ounce of sugar and 1 milligram of vitamin C. Each ounce of orange juice contains 0.25 ounce of sugar and 3 milligrams of vitamin C. It costs Bevco 2 cents to produce an ounce of orange soda and 3 cents to produce an ounce of orange juice. Bevco's marketing department has decided that each 10-ounce bottle of orange must contain at least 20 milligrams of vitamin C and at most 4 ounces of sugar. Use linear programming to determine how Bevco can meet the marketing department's requirement at minimum cost. So from that example, we have obtained these decision variables. So x1 represents the number of ounces of orange soda per bottle of orange. x2 is the number of ounces of orange juice per bottle of orange, and then z is for the total minimum cost. Then the objective function is mean z is equal to 2x1 plus 3x2. Then we have 3 constraints. The first is for the sugar requirement. So that is 0.5x1 plus 0.25x2 is less than or equal to 4. For the vitamin C requirement, that is x1 plus 3x2 is greater than or equal to 20. And the content per bottle is x1 plus x2 is equal to 10. Then all the variables, so x1 and x2, are greater than or equal to 0. So as with the simplex method, the Big M technique starts with the LP in equation form or standard form. So we have to convert those equations into its standard form. If the equation does not contain a positive slack variable to perform the role of a basic variable, an artificial variable, which is sometimes called a dummy variable, then we use the letter R as added to the equation. So you must always remember that when the constraint has an inequality sign of less than or equal to convert it into its standard form, you have to add a positive slack. So we use that in the simplex method. And if the constraint has an inequality sign of greater than or equal to, so the left side is deemed to be greater than the right side, you have to add a negative slack. And since this is negative, it cannot be a basic variable, you have to add an artificial variable. So if the sign is greater than or equal to convert the constraint into its standard form, you have to add a negative s, then a positive r. If the equation has an equal sign, you only need to add a positive r, or an artificial variable. So that is the shortcut or the notations in converting constraints into its standard form. So here is the primal form for the example number 7, or for the Orange by Bevco. We have to convert these equations into its standard form. So same as in the simplex method, so we have to deal with this one by one. So for the first constraint, yung 1/2 x1 plus 1/4 x2 is less than or equal to 4. its standard form becomes 1/2 x1 plus 1/4 x2 plus s1 is equal to 4. So since the inequality sign is less than or equal to, just like in the simplex method, you just have to add plus s1. So for the second constraint, the inequality sign is greater than or equal to. So you have to add a negative slope and then a positive r. So the equation becomes x1 plus 3x2 minus s2 plus r1 is equal to 20. Then yung third constraint, x1 plus x2 is equal to 10, so equal sign. So you just have to add another alternative variable. So the equation becomes x1 plus x2 plus r2 is equal to 10. Then, list down all variables. They should be greater than or equal to 0. Then, for us to be able to dispose these artificial variables during later iteration, we have to assign penalties to them to force their values to become 0 at the final iteration. So here is the penalty rule for the artificial variables. We will use another variable or another letter, which is m. A sufficiently large positive value, mathematically m approaches infinity. The objective coefficient of an artificial variable represents an appropriate penalty if, so we have two choices. So we have to multiply the artificial variable by negative m if the problem is maximization, and we have to multiply it by positive m if it is a minimization problem. Then the product of these m's and the artificial variables will be added to the original objective function. So for example, in our example here, so since we have two artificial variables, we will multiply these variables by m and then we will add them to the original objective function. So the original objective function now becomes mean z is equal to 2x1 plus 3x2 plus mr1 plus mr2. So we added two terms since we have two alternative variables here. So if you have r3 or r4, you need to add plus mr3 plus mr4 and so on. So we have to transfer all the terms to the left side, so those terms becomes negative. So the final standard form for the objective function now becomes c minus 2x1 minus 3x2 minus mr1 minus mr2 is equal to 0. Then after successfully converting all those equations into their standard forms, we will now go to the iterations. So same as in the simplex method, you will always start with an initial tableau. So the initial tableau contains the basic, then the z for the 0. Then for the first constraint, the basic variable will be s1, same as in the simplex method. Then for the second constraint, since s2 is negative, it cannot play the role of a basic variable, so we will use r1. Then for the third constraint, that is r2. Then the column headings, you will put there all your identified variables. So those are x1, x2, s1, s2, r1, r2, and rhs. And then you will plot all those values or all those coefficients in the initial tableau. So for the 0, or the objective function, so under x1 is negative 2 minus 3x2. Then there are no values for s1 and s2. And for r1 and r2, you will put there the coefficients. So you will put the letter m's. So r1 has negative m, r2 has negative m, and rhs is 0. Then for s1, that is 1/2 x1 plus 1/4 x2 plus s1 is equal to 4. For the second constraint, that is x1 plus 3x2 minus s2, so that is negative 1 under s2, plus R1 is equal to 20. Then for the last constraint, that is x1 plus x2 plus R2 is equal to 10. Then, unlike in the simplex method, a new initial tableau must be constructed first before proceeding with the usual iterations using the Gauss-Jordan computations. So, in doing a new initial tableau, you will need this equation. So, new zero coefficient is equal to the old zero coefficient plus the summation of the R sub n row coefficients multiplied by m. So to create a new initial tableau, you will use this equation, but please note that this is a plus sign since we are dealing with a minimization problem. But if you are solving a max problem using the Big If technique, you will replace this plus sign with a minus sign. So the minus sign is for max problems. So to create a new initial tableau, you need the initial tableau and this equation. So yung new zero coefficient is equal to the old zero coefficient plus the summation of R and row coefficients times m. So the Rn's are the rows of R1 and R2. Or if you have other artificial variables, you will need all of those. So the new initial tableau is just the same as the initial tableau except for the values under the zero. So you will find new values that will be placed in the zero using this equation. So for example, the value that you will place under x1 is the old zero coefficient, which is negative 2, plus the summation of the R and row coefficients. So R1 times m plus R2 times m. So simply, the equation is negative 2 plus 1. So 1 is the R1 row coefficient times m plus the R2 row coefficient is also 1 times m. So the resulting value is negative 2 plus 2m. Then under x2, so the old zero coefficient is negative 3. So here is negative 3 plus R1 row coefficient is 3 times m plus R2 row coefficient is 1 times m. So the answer is negative 3 plus 4m. Under S1, the old zero coefficient is 0 plus 0 times m. Here is 0 times m plus 0 times m. That is 0. Under S2, so we have 0 plus negative 1 times m plus 0 times m. So that is negative m. For R1, we have negative m plus 1 times m plus 0 times m. The resulting value is 0. And under R2, we have negative m plus 0 times m plus 1 times m. So that is equal to 0. And for the RHS, we have 0 plus 20 times m plus 10 times m. So the resulting value is 30m. So here is our new initial tableau. And then, after creating the new initial tableau, you have to identify two variables again to proceed with the iterations. So first is the entering variable. Then, during the simplex method, here is the category in identifying the entering variable. It is the most negative value from the zero. That is for maximization problems. Then, for minimization problems, the criteria is it should be the most positive value from the zero. Then, the column containing that positive value or that negative value is classified as the pivot column. Then after, you need to identify a leaving variable. So same as in the simplex method, that is the least positive ratio. So the ratio is the RHS values divided by the corresponding values from the pivot column. And then the entire row containing the least positive ratio will be regarded as the pivot row. So we need to identify those two values to proceed with the iterations. So here is the new initial tableau. And then you need to identify the most positive value in the zero. But how will you identify a positive value if the values has letters, may letter M? So to identify the most positive value, we have to assume that M is 100. So the assumption is only used in identifying the entering variable. If you will do the Gauss-Jordan computations, you will compute the values with the M's. So you will compute them as they are. So you will not change M's into 100. So we will only assume that the value of M is 100 in identifying the entering variable, not in the Gauss-Jordan computations. So to identify the entering variable, assume that M is 100. So you will substitute the value of M in these terms, then identify the resulting value. So for x1, that is negative 2 plus 2 times 100. So the value is 198. For x2, that is negative 3 plus 400. So that is 397. For s1, that is 0. For S2, that is negative 100, R1 is 0, and R2 is 0. So the most positive value in the 0 is 397. So x2 becomes our entering variable. Then after, we need to identify the leaving variable, which has the least positive ratio. So we will get the ratio. We divide the RHS terms by the corresponding values in the pivot column. So we don't usually use Z as a leaving variable. So for the S1 row, that is 4 divided by 1/4, so the value is 16. For R1, that is 20 divided by 3, so that is 6.67. And for R2, that is 10 divided by 1. So the resulting value is 10. And then the least positive ratio is 6.67, and R1 is our leaving variable. So after identifying the entering variable and the leaving variable, you will use the usual Gauss-Jordan computations, the same computations or the same way of computations that we used in the simplex method. And then proceed to the initial tableau or the iteration 1. So the iteration 1 tableau looks like this. So I will not compute them one by one. So for example, yung value na to, this value came from negative 2 plus 2m minus negative 3 plus 4m times 1/3. So you will compute for the values with the m's. So you will not replace the m's by 100. You will compute them as they are. So after successfully computing the values for iteration 1, you will look again for a possible entering variable. You will assume again that m is 100. So for the value of x1, substitute 100 for m. So that is negative 1 plus 2/3 times 100. So the resulting value is 65.67. For s2, that is 0. For s1, that is 0. For s2, that is negative 1 plus 1/3 times 100, or 32.33. For r1, 1 minus 4/3 times 100, or negative 132.33. and for R2, that is 0. So our most positive value in the 0 is 65.67. So this is our entering variable, x1. Then get the ratio to identify the least positive ratio for the living variable. So for S1, that is 7/3 divided by 5/12. So or 5.6. For X2, that is 20/3 divided by 1/3. So that is 20. And then 10/3 over 2/3 for R2. So that is 5. And the least positive ratio is 5. So R2 is our living variable. So after, perform the Gauss-Jordan computations on your own and then proceed to iteration 2. So this is the resulting values for iteration 2. So check if you still have positive values in the 0. So our S2 is -1/2. Our R1 is 1/2 minus 100. So that is -99.5. R2 is 3/2 minus 100. So that is -98.5. So we don't have any positive values in the 0. So we're looking for positive values since this is a minimization problem. If this is a max problem, so you need to find the most negative value. So if this is a max problem, the R1 will be an entering variable. But since this is a minimization problem, and since there are no positive values in the 0, the iteration ends. So from the last iteration, we have found that the values of x1 and x2 are both 5. S1 is 1/4. S2 is 0. Then R1 and R2, so we have successfully disposed our artificial variables. If it happens that you cannot dispose R1 and R2 from the basic, it means that your problem has no feasible solution. But since R1 and R2 are both 0, this is an optimal solution. And then Z is 25. So if you want to check your values, you can do the checking. So same as in the simplex method, you can do this. You have to find if the values are equal to one another. So that is the Big M technique.